Good day, everybody. I'd say good afternoon, but that's just here in the East Coast. If so, depending on where you are in the world, you could be still be in the morning. So, good morning, good afternoon. Basically, happy Tuesday, everybody. John Barba here with Takeo Comfort Solutions, and thank you for joining us for another Takeo Tuesday session. I'm joined by my dear friends and colleagues, Dave Holdorf and Rick Mayo. Say hi, guys.
Hello.
Howdy do.
There we go. And we've got a pretty cool session planned for you all today. We're going to talk about three-speed circulators. Maybe it sounds like we're going a little bit retro here, but we're going to talk about three-speed circulators and do they in fact still have a place in our world? And I think that the obvious answer is yes, they do.
Sure.
I want to do a quick inventory here of everybody. We got a bunch of people online. I want to make sure everybody can A, hear us, and B, know how to ask questions. So on your control panel, you should see a little orange arrow, and if that arrow is pointing to the left, click on it, and that will expand your control panel. And in that control panel, you'll see a chat section, and that's going to be how you ask questions. And I see Doug and Eric and Jonathan have already figured that part out. That section where you ask questions, please type in a hi, hello, how are you? Just so I know you guys can hear me, and I know you guys know how to, and ladies know how to ask questions. And boy, oh boy, that's getting populated in a hurry. Gotta love it. Excellent, excellent, excellent. Thank you, everybody, for that. So this asking questions part is really important. This is how I believe you are all going to get the most out of this program. So I encourage you to ask questions. Both Dave and Rick will be monitoring the question section. And every so often we'll take a little, pause for the cause here and ask a few, and answer a few questions. So don't feel you have to wait till the very end of the program to ask the question. Ask them as they come up, and we'll answer them as best we can as they come up as well. The other thing I'd encourage you to do, since it's maybe been a while since we've done this, is make sure you have a pad of paper and a pen handy with you, and treat this program like you would treat a live in-person webinar. Webinars are fun. You can see me, but I can't see you, and you may get a little. If it's easy to check Facebook, it's to look at your phone or do whatever it is you do to multitask while we're on here, and that takes attention away from what we're talking about. So I would ask you, if you can, just try to resist that impulse as much as possible. We'll do our best to keep it interesting for you, so you don't want to do that. But if you grab a pad of paper and a pen and take notes while we're going through this, that'll be fantastic. That'll help you stay engaged. The other thing I want to say is we are recording this session. You will get an email tomorrow, a follow-up email tomorrow with a link to the registration, or a link to the recording rather, as well as a certificate of attendance that you can download. So that'll be there for you as well. But you'll get a link to the recording that you can watch as many times as you wish. But again, to get the most out of it as we're going through it, let's take those notes, ask those questions, and stay engaged. So without any further ado, let's get started on this this webinar. Do three-speed circulators still have a place? I think that's a really good question. The whole industry has been ECM centric and ECM crazy over the past several years, to the point where whenever we talk about a three-speed circulator, we'll always get a response as, well, why not just use a variable speed pump and be done with it? Why are we wasting our time with this? Because this is old school technology. Well, yeah, I wouldn't say old school technology, but this is, fixed speed circulators. And just to be clear, three-speed circulators are in fact fixed speed circulators. They just have three speeds, all right? You can pick 1, 2, or 3, but they are fixed speed circulators. They still have a place. In fact, if we were to actually do a head count of how many fixed speed circulators that are sold in the residential hydronics industry versus the number of variable speed circulators sold in the hydronics industry, it's not even close. It's really not close. The ECM market is growing, the variable speed market is growing, and in many cases, that market is seeded by utility company rebates, where they're encouraging you to use a variable speed ECM circulator because it uses less electricity than a fixed speed counterpart. In those areas, yes, we're seeing a huge number of variable speed circulators sold, but outside of that, outside of areas where those things are actually being implemented, then no, it's not that's not the equation. We're seeing the fixed speed market dominating the ECM variable speed market. So as a result, and it's just a financial thing at this point, is that we do see fixed speed circulators, 3-speed circulators, as well as single speed circulators still ruling the roost. So yes, they do still have a place. Now, this isn't a webinar on how to convert that, how to convert fixed speed to variable speed. This is a webinar instead on really understanding 3-speed circulators and making sure you use them for the right reasons and not the wrong reasons, because there are a lot of wrong reasons out there. People ask me, what are those wrong reasons? Well, I'll preface it by saying this right here. If my answers frighten you, you should cease asking scary questions. I've been accused in other sessions of being anti 3-speed. And I've done a lot of soul searching on that, and I could see why people might think that, because I tend to blast 3-speed. But it's not the 3-speed circulator per se that I have an issue with. It's how they've been sold. It's how, you know, the manufacturers have actually sold them to you. And one of the most common, and you tell me, when someone has tried to sell you a 3-speed circulator, what has been the message? The message by and large has been not so much that it's you know, right for the application. It's more along the lines of, this is the only pump you'll ever need. It doesn't have 1 speed, it doesn't have 2 speeds, it's got 3 speeds. It'll do everything. Keep it on your truck for service. It's the ultimate replacement pump because it has 3 speeds. Hey, wholesalers, put this on your shelves. It replaces all these different SKUs with 1 circulator. It's the only pump you'll ever need. It does everything. It's a very compelling and very happy story. It's largely nonsense, but it's a very good story. That's been the problem I've had with that. And the fact that people have adopted that as saying, well, I use them all the time because it does everything I need. Then you see them almost invariably set to high speed. So instead of you making use of low and medium, I got 3-speed. If low is good, medium's better. If medium's better, then high speed's got to be the best. I'll just set it to high speed. I don't have any problems. I'll get the hell out of here and we're done. Well, the problems that something like that can create are not obvious or immediate. They are more long-term. Freezing to death isn't one of those problems. So people tend to think, well, if it's not freezing to death, it must work. This is where it gets interesting. I mean, folks that, you know, as an industry, we've got wonderful craftsmen. You guys out there are wonderful craftsmen. You're excellent technicians. You do work that when I worked with the tools, I couldn't even begin to think about doing because I just didn't have the skill set that you guys have. But we see people out there who invariably make everything, make their mechanical rooms look like they belong in a palace. Absolutely incredible. They use the best condensing boiler technology they can. They use a high performance air eliminator, everything straight plumb and dead sexy. And then they'll throw in a 3-speed pump set to high speed without even thinking about it. What we want to do today is get you to think about it. Okay. So think about, why do you use 3-speed pumps? These are some of the answers that I've got. I ask people all the time who, you know, if they use them, I said, great, why do you use them? And these are some of the real answers that we've received over the years. Most common one is, well, it makes pump selection easy. Makes it wicked easy. I don't have to think. I just use, it's a simple transaction. Give me a pump, they give me a 3-speed. I'm good to go because it's got 3 speeds. It makes pump selection easy. This one I've actually gotten. And this one makes me chuckle a little bit. Well, it's a better value. It's a better deal. I get 3 speeds for the same price as I get a single speed. That's like getting 2 speeds for free. It's like it's somehow it's conveyed. It's looked at as a better deal. All right, I get 3 speeds for the price of 1. My favorite one was this one. Why do you use 3-speed pumps? It's because you don't make any 4 speeds. You make a 4-speed pump, I'll buy that one. That's been my favorite. Then we'd like to ask, well, if you use a 3-speed circulator, how do you know what speed to use? How do you pick the right speed? Well, we've heard this one. I start it high, and if it makes noise, I turn it down until it stops. Okay, that's reasonable. All right. And then the other one is, well, I start it low and I turn it up till it starts making noise. Then I know I've gone too far. Okay, fair enough. And then this one's my absolute favorite, and this is a real answer, where a guy says, if I have a gas boiler, I set it to high. If I have an oil boiler, I set it to low because everybody knows you get more BTUs out of a gallon of oil than you do out of a therm of gas. I guess that's the rationale. And if I got it on an indirect, I put it to medium. Hey, it's worked. It's worked. So I just stick with it. There's not a whole lot of science behind it other than a guess. My personal favorite, which we don't hear all that often, is after careful calculation of flow and head, I select the speed which has the pump curve that best covers the requirements of each job. Said very few people ever. A lot of people believe that, but you just do your own soul searching. I know I see guys pictures. We see pictures all the time on Facebook groups, etc., where they show these beautiful jobs with 3-speed pumps, and if you look really close, every last one of them set to high because it's contractor no callback mode. If I set it to high, I know no one's going to be cold. There may be other issues, but I know no one's going to be cold. So that's kind of the reality. And really what we're talking about is guessing. And this is from Sherlock Holmes, Sir Arthur Conan Doyle. I never guess. It is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. It's a powerful thing. It's a very powerful thing. And one of the things about hydronics is we can break it down into facts because we can do math. All right, we can do math, and there's no reason to be afraid of math. The two math formulas we're going to deal with are ridiculously simple today, and they'll help you get to the truth. All right, they'll help you get to the truth. The first math formula is what we call the universal hydronics formula. We talk about this all the time. GPM equals BTUH divided by the product of delta T times 500. That tells us how to figure out the flow rate you need, the gallons per minute that you need to provide to deliver the BTUs required. So GPM equals BTUH divided by your design for delta T, the temperature drop of the fluid as it goes through the system, times 500, a mathematical constant that comes from multiplying the weight of 1 gallon of water, 8.33 pounds, times the number of minutes in an hour, that's 60, times the specific gravity of the fluid and the specific heat of the fluid. 100% water has a specific gravity of 1 and a specific heat of 1. 8.33 times 60 times 1 is 499.8. We'll call it 500. Glycol changes that, but we're going to deal with 500. The other math formula is this one. It's estimating head loss or friction loss through the piping circuit. What you do there, let's look at a fin tube baseboard application where you estimate as best you can the measured length, meaning from the outlet side of the circulator all the way around the system through the inlet side of the circulator. That's your measured length. To allow for valves and fittings and stuff that's in the way, you're going to multiply that by 1.5. You're adding 50% to allow for the valves and fittings. That gives you something called your total developed length. To estimate the head, you multiply your total developed length by 0.04, which represents 4 feet of head loss for every 100 feet of straight, properly sized pipe. So multiply your total developed length times 0.04. That will give you your estimated head loss. So once you know flow and head loss, you can now start to look at a pump performance curve and see what makes the most sense for the job you're looking at. Okay, see where you're at. All right, and as you notice the asterisks here, I want to make sure that neither of those formulas will harm puppies, kittens, or bunnies. So those signs say every time you do math, a kitten dies, a puppy dies, a bunny dies. No, that's not true. So you're not hurting any puppies or anything like that. All right, very good. How are we doing for questions out there, Dave, or comments? Are we, Dave and Rick, anything good coming in?
Well, we had one question come in from Anthony who was asking about the percentage increase about 3 speeds, for each different speed. And I said that we're going to review the pump curves for each model. We have different percentages, so it's not an equal breakdown. It can do this, and so we're just going to break it into thirds. It's all more based upon application and which model that we have in there. So that was a good question, and Anthony. And then Rick, I'll let you grab the second one there.
Emil has got a question about, what number do we use for glycol? And I responded to him, just said, hey, there's a couple of variables there. We need to know what temperature and we need to know what mixed glycol, and then we can come up with a number. But the number will range from maybe 485 down all the way down to like 450 for the constant glycol mixes, depending on the mixture and the temperature. So.
Very good. All right, excellent. Keep those questions coming in, folks, and want to make sure that the pace is okay and everything else is working. And again, any questions you have, type them in as they come along. Excellent. And just so you know, we are protecting puppies, kittens, and bunnies. So here's maybe this can approach one of the questions. This is a pair of 3-speed circulator pump performance curves from Takeo. We have our 0015 and our 0010. The 0015 is kind of like your industry standard pump curve. The 0015, the Grundfos 1558, B&G NRF 22, all of them have essentially the same pump performance curves. You might find some might be a little higher on the 0 gallons per minute end. Some might be a little farther out on the 18 gallons per minute end. But in terms of the actual sweet spot of the pump performance curves, which we're going to talk about being maybe right in that area or thereabouts, they're all really close to the same in terms of performance. All right. You know, a lot of people get wrapped up as well. I'm way higher up here. That's better. But if you ever have a system where you got 1 gallon a minute at 18 feet ahead, we really need to chat, okay, in terms of design. The other circulator, the 0010, is a service pump that was actually designed and intended for use as a replacement pump for old B&G 100s or old Takeo 110s, as you'll see as we go through this presentation. So that's kind of what that particular circulator was intended for. Let's do some examples so you can see when we need to do what. So let's just look at a fin tube baseboard zone. I got a wicked big zone of fin tube baseboard. I gotta have high speed, right? And we're looking at using the circulator as a zone pump, not with zone valves, just as a single zone pump. Big old honking zone of baseboard, man. I gotta have high speed, right? Well, let's take a look. Let's do some math and see where we're at. So let's say this is a 3/4 inch copper zone, and I've got 40,000 BTUs worth of baseboard on it. So that's a big honking zone, right? Actually, 40,000 is the most you can have on a 3/4 inch zone. So we're talking a big freaking zone right here. All right. That equates to about 80 feet of baseboard. The overall run of that zone is 160 feet. So it's 80 feet of baseboard plus 80 feet of pipe. That's 160 feet altogether. So what I want to do now is turn this into flow and head so I can pick my pump. So the flow rate, simply use the universal hydronics formula. 40,000 BTUs divided by my delta T of 20, which is what we're designing for, times 500 is 10,000, right? So 40,000 divided by 10,000, that gives me 4 gallons per minute. All right. Now that's my target flow rate. So right down here, I'm looking for 4 gallons a minute. Now we want to estimate our head loss. So for head loss, I've got 160 feet, right? I want to allow for fittings and stuff that's in the way. I'm going to multiply that by 1.5 to allow for fittings, and then I'm going to divide that number by 0.04, 4 feet of head for every 100 feet of straight, properly sized pipe. So 160 times 1.5 divided by 0.04 is going to give me an estimated head loss of 9.6 feet. 9.6 feet. So now I can look at my 3-speed chart and find my requirement. 4 gallons a minute, 9.6 feet ahead, bada bing, there I am. So taking a look at that, what speed would you select? For a big honking zone that's pretty long, 160 feet is a long zone. So clearly the choice here is going to be medium speed. Now the question is, how many of you would have automatically said, oh boy, for that big of a zone, I'm going right to high and I'm going to be done with it. If you went right to high and were done with it, would you deliver the BTUs needed? Absolutely, you absolutely would. So what's the problem? Well, let's take a look. Let's take a look. What I've outlined here are different points on a plot for a system curve. And we've talked about system curves in our webinars in the past, and there's a math formula for figuring this out. Part of that math formula we just did. At 4 gallons a minute, I'm at 9.6 feet ahead. Based on that, mathematically speaking, I can calculate other points. At 1 gallon a minute, what would the head loss be? At 2 gallons a minute, what would it be? At 3, what would it be? 4, I know. At 5, what would it be? I can math that stuff out, put those points on the plot, and then connect the dots like so. Why the dots are important is because where the system curve intersects the pump performance curves that I'm using is where the system's going to actually really and for true operate. Okay. So if I were to look at this and say, well, if I did pick low speed, I'd be right here. And that's about 3.5 gallons a minute at 7 feet ahead. That's going to work most of the heating season, but when it gets real cold and when I need my 40,000 BTUs or 4 gallons a minute, I might be a little on the cold side. That's a possibility. Medium speed probably makes the most sense, and I'm going to intersect right here at 4.5 gallons a minute at almost 12 feet ahead. Okay, that's going to, that's really not a badly sized fixed speed pump compared to where I need to be. But if I said, the hell with it, I'm going all the way up to high, I'm now at 5 gallons a minute and 14.5 feet ahead. I'll tell you this, when we're talking about a zone pump, 14.5 feet ahead, 12 feet ahead, doesn't make any difference. What we're concerned about is the flow rate. So as a zone pump, we're not overly concerned about the head. We're much more concerned about these two numbers right here. All right, flow. And here's why. Will it work? Absolutely. Absolutely. In both cases, in medium speed and high speed, we're going to deliver the BTUs. It's going to work, and it's going to work just fine. However, let's revamp this universal hydronics formula, and let's look at delta T equals BTUH divided by GPM divided by 500. Okay, the puppies and bunnies might be getting annoyed at this point, but they're still not in danger. You may not have to do this math formula yourself, but I just want to show you what the results would be of picking medium versus picking high. So if I was at high speed, I'm at about 5 gallons a minute, right? So 40,000 BTUs divided by 5 gallons a minute divided by 500, that tells me the very best delta T I'm going to see here is 16 degrees. So that could be the water goes out at 180, instead of coming back at 160, it comes back at 164. That's pretty good. That's not bad. All right. However, if I actually set it to medium speed, my delta T will be 18 degrees. Keeping the delta T between what goes out and what comes back as wide as possible for as much of the time as we can during the course of a heating season, that's going to help the boiler work better, work more efficiently, and work more effectively. We're going to reduce short cycling as much as we can in either a cast iron or a condensing boiler. And the wider we keep it with a condensing boiler, the more that boiler is going to condense as it gets down to lower temperatures. So it's to our benefit at this point to do a little bit of math, look at a pump curve chart and say, you know what, medium's going to be better than high. Because you also have to understand that 16 and 18, you're only going to see that once, and that's under design conditions, quote unquote, coldest day of the year. The warmer it gets out, the smaller those numbers are going to be. So at a 50% load, let's say, say your outdoor design temperature is 0, let's say when it's 35 degrees outside, then this number is going to be 8 and this number is going to be 9. 9 is better than 8. Is there a big difference in this case? Not a huge one, but let's use this circulator to the best of its capabilities and keep the delta T as wide as possible for as much time as we possibly can. All right, Dave and Rick, any questions pop up in that time frame?
Yes, we found. Go ahead, Rick.
You have a question. Jonathan was clarifying. I wasn't sure. I caught it as well, but I thought maybe you were doing a reciprocal. But go back to where you did 160 foot times 1.5, and then you divided by 0.04, not times. And he's asking you why you did that, because normally you times it again.
Oh, duh, I'm sorry, that was a typo. Excuse me. Yes, yeah. Now I'm looking at, yes. I apologize. That was a typo. That it should be times 0.04, not divided. So good catch, Jonathan. Thank you for that. That was a good catch. And there's a question: where did it come? Where did it come from? 0.04 represents 4 feet of head for every 100 feet of straight, properly sized pipe. So it's just at the maximum flow rate for that size of pipe. All right. Another question here about it's ideal to do the math, but on a lot of retrofits with an old existing system, You can't really do accurate calculations on length of pipe. Usually these are single zones. What's a good way to estimate? Estimating is really what we're talking about. And that's, and in many cases, what we're talking about here for estimating is, here's the outlet flange of the pipe. I'm going up 10 feet and over 10 feet. That's 20 feet. I'm going down 40 feet. So 20 and 40 is 60. I'm going over 20. That's 80. I'm coming back 40 feet. That's 120. I'm coming over 20 feet. Okay, that's 130 or whatever. And I'm coming down 10 feet. That's 140. That may very well be the best you can do. All right, that very well may be the best you can do here. But that's the least you should do. That's the bare minimum effort you should put into this. If you can do more, you can do more. You can't get in and measure down to the gnat's whisker. That's impossible in a retrofit, but you can estimate. How long could this zone possibly be? So at least you've got something to base your calculations off of, as opposed to, I'm just going to take, I'm just going to put in the biggest thing I can and hope for the best. That's
Right.
not a strategy in my book.
Yeah, when you're doing that estimate there, obviously we don't want you to spend a tremendous amount of time trying to size it. You know, you've got an existing project, you need to get the heat back going again, and you want to make sure you got the right circulator. So if you're going to choose a circulator and you're going to estimate that, don't spend a lot of time at it. All right, and busting open walls. If your estimate length of pipe has a number other than a 0 and 5, you might have spent too much time. Okay, you know, because what we're doing is multiplying it by 1.5 because we don't know all the fittings and all the pressure drops that you have associated with that. So, yeah, it is still going to be best guess, and it is still going to have that little bit of extra fudge into that number. It's going to be a little elevated for you on that head loss, so you will be safe. Do not add more. We've already done that for you with that formula there.
Right. And here's the thing too, in terms of best guess, it's really relying on your experience and knowledge of piping. I mean, everybody in here has been in a house under construction and has run pipe through houses. So you can use your intuition and your experience to say, you know, I'm gonna presume. And you do have to add a little bit for the unknown, but you know, to get from here to there, it can only be that long, you know? So you use your skill, you use your levels of understanding on how pipe is run and how homes are built to make those judgment calls. So it's not so much a guess as it is an educated, intuitive deduction, if you will, which sounds better, doesn't it? Alrighty. How about a zone valve job? I'm going to need high speed for a zone valve job, right? Right? Because I got all those zone valves. I mean, it's one pump and all that pipe and all those zones. I'm going to need high speed there, right? Well, here's an important point to understand when it comes to zone valves. A zone valve system is a parallel piping system. And in a parallel piping system, you only need to size the circulator for the worst case head loss zone. You don't have to figure the head loss through each zone, add them together, and there's your head. You simply figure out what's the worst case zone, and I'll size my circulator to that zone. Because in a parallel piping system, if my circulator can overcome the worst case head loss zone, it can most certainly overcome all the others, right? It can most certainly overcome all the others because they're not as long. You don't add head together. You do add flow together. We don't add head together. We just pick the worst case one. We do add the flow rate of each zone together because flow is cumulative. At some point, that circulator is going to have to deliver all of the flow required for the system with all zones calling, but it's only going to have to overcome the worst case head loss zone. Oftentimes, that's a tough concept for some folks to get their head around, but it saves you from oversizing a circulator. You just don't have to, you know, I got a, this zone has 4 feet ahead, this one has 5 feet ahead, and this one has 6 feet ahead. All right, 4, 6, I don't have to have 15 feet ahead. I just have to have 6 feet ahead because 6 feet ahead it will do 5 feet ahead and 4 feet ahead, if that makes sense to you. So any questions on that? If you're not quite sure, let us know and we'll dive a little deeper into it. But that's an important thing to remember when sizing a circulator for zone valves. Which brings us to the Taco Tuesday Mystery Theater. I don't know about you, but I love me some mysteries, man. And this guy, Columbo, was, you know, being of Italian descent, Columbo was my guy, all right? He was my guy in the 70s and then in the late 80s, early 90s when they had the reboot. I love me some Lieutenant Columbo. So I'm going to go get my, I didn't get my rain jacket, my raincoat. I should have brought it with me, but let's talk about Lieutenant Colombo, and let's talk about a mystery. All right. This was in Connecticut several years ago. Full boiler change out. All right. The guy did everything. It was all a new 90,000 BTU boiler, all new accessories. It was a zone valve job. Okay. There were 5 zones on this job, 5 zone valves, but he did completely redid the boiler, completely redid the system. He had this pumping away. He was doing everything right in the installation. All right. But after the change, the zone valves banged like crazy. They didn't bang before. Okay. Before, nice, quiet, everybody was happy. After the change out, the zone valves banged like crazy to the point where the homeowners were complaining, they were holding up payment, yada yada yada. They tried everything. All right. So here's a little bit more background, okay, on this particular job. When we want to figure out what's going on, we got to think about Colombo. We got to ask questions. What was there before? What changed? Well, obviously the new boiler changed, all the new accessories changed. That shouldn't create have zone valves banging where they weren't banging before. What was different? Well, here's what was different. The original circulator was an old Taco 110. That's the large 3-piece circulator. It's basically akin to a B&G 100, if you will. And here's the pump curve. As you can see, the pump curve for a B&G 110, you're maxing out at about 7 feet ahead here. It'll go out to about 30 gallons a minute, but we're talking about 7 feet ahead, okay? It was replaced with a Taco 0015. And because it was a zone valve job and kind of a big structure, they said, well, I better set it to high. Now, high speed, we're talking 16 feet ahead, and in excess of 16 feet ahead, out to about 18 gallons a minute. Are we starting to see a bit of a disconnect here? You got a flat curve pump versus a steep curve pump. You got to understand when you're using 3-speed pumps, understand how they interact with existing system dynamics. This is where I start to really lose it when people say, I use this pump all the time for service. It has 3 speeds. It's the only pump I'll ever need. If you understand system dynamics, you know the fallacy of that statement. Okay, and here is a graphic illustration of that. So here's what happened. All right. So what happened here is, now I'll take it one step further, then we'll get into some analysis. The next step was they thought that the Taco circulator was causing the problem. It was banging, all right, and it banged on all 3 speeds. So they figured, well, the Taco circulator must be the problem. We're going to put in a Grundfos 1558 3-speed. Okay. Well, as you can see, the pump curves are essentially the same. It was still banging on all 3 speeds. So the question we have to ask now, what would Lieutenant Colombo ask? Why are they banging? What's causing them to bang? They weren't banging with the Taco 110, but with the Taco 0015 and with the Grundfos 1558, these things are banging. Why? What could possibly make them bang? Well, here, let's take a look. The total load was 80,000 BTUs, or 8 GPM, based on our knowledge of the universal hydronics formula. And the zones were pretty much equally sized, about 16,000 BTUs apiece. So let's see this system curve, pump curve thing that we talked about before. We were about 8 gallons a minute at 5 feet ahead. That's the requirement. Now remember, we have system curves, right? The system will operate where the system curve intersects the pump curve. So really what we're talking about here is maybe working at this point right here, a little over 10 gallons a minute. Our delta T might be a little bit smaller. But look at this. We're probably at about 6 to 7 feet of head being created by the pump. With just one zone calling 1.6 gallons a minute at 5 feet ahead, we're probably right about here. Extend that system curve up, and now we're at about maybe 7.5. So what we're dealing with here is a big change in flow as zone valves close, but a very small change in head pressure differential created by the circulator. Now let's compare that to either of the other 2 circulators that we were using. 8 gallons a minute at 5 feet ahead, here's the requirement. Well, low obviously isn't going to work here, But here's the system curve. Okay, here's the system curve. With all zones calling, with all my zones calling, we're out here at about what looks to be 9.5 gallons a minute at about 7 feet ahead, or at about a little over 11 gallons a minute at about a little over 9 feet ahead. Compare that now to one zone calling, my smallest zone calling, which would be right here. In this case, now I'm intersecting way the heck up here, all right, at about, let's say, 2 to 2.5 gallons a minute at 13 feet ahead, or 3 gallons a minute at 15.5 feet ahead. So Lieutenant Colombo asked the question, when do the zone valves bang? Do they bang when all zones were open and then some of them closed? Or did it bang when maybe 2 or 3 zones were open and then 1 or 2 closed? Well, the answer came back, well, when all zones calling and a zone closed, they didn't make any noise. It was when 1 or 2 zones were open and then 1 closed that they started to bang like hell. What does this tell us? It tells us this up here is causing the zone valves to bang. When zone valves close against that kind of head pressure differential, that's when they start to bang. That's why we learned this years and years ago, that steep curve pumps like the 0015 3-speed, like the Grundfos 1558 3-speed and others, steep curve pumps and zone valves go together like ice cream and tuna fish. Flat curve pumps like the B&G 100, the Taco 110, the 0010 3-speed, heck, the Taco 007, flat curve pumps like that go together like tuna fish and mayonnaise, or cookies and or cake and ice cream, whichever analogy you're more comfortable with. All right. So in this case, that notion that 3-speed pumps are the only pumps you'll ever need requires an understanding of system dynamics. What am I hooking it up to? All right. What am I hooking it up to? And is the curve appropriate for the application? That's between your ears. That's your knowledge. So even though one of the things we talked about was a retrofit or a replacement, I got a dead pump and I need to replace it. Well, is it a zone valve job? Yeah. If it's a zone valve job, if you want a 3-speed pump, make sure you're looking at the right 3-speed pump and not the wrong 3-speed pump. And that's the story. That's the way to think about it. That keeps you from creating a problem where there was none before. All right. And again, we had the same issue here with the Grundfos. All right. Same thing, the exact same problem. So, it's just how these things actually work. Okay. And as the lieutenant says, just one more thing here, if we did use the 0010 medium speed, happy, joy. All right. Okay. We're not going to have a banging problem there. And in fact, the simpler solution for this job and what we told the contractor to do was to simply put in a 007, because the 007 solved the problem as well. We stayed below 10 feet ahead, which for this particular application appeared to be the magic number to keep the zone valves from banging. And that's what did it. Guys, how are we doing for questions out there?
Good.
Doing pretty good. Just got one in from Doug, and he says, well, what if you would have slowed down the valves, the speed of the valves from closing to help with the banging? And
meaning using a slow acting zone valve, like the Taco 570s series.
Right, correct. Yep, that's what he's looking for. So I would say that does help until it gets still to that last little bit. It could still make some noise. It could make a whooshing noise that you could hear. May not bang as much as you hear with the quick closing valves. But obviously, think about that for a second. If you needed to change the zone valve, wouldn't it be easier to change the circulator instead if you had a couple of isolation flanges and put in the right pump rather than pulling out zone valves, drain the system down, put a new valve in, purge, and all that other jazz? It might be better off just to change the circulator. And John's going to show you that right now too.
And I think that the instance there might be the difference between banging here versus banging here, because the interesting thing is this job that we're referencing did have the 571 zone valves in there. So you're changing a zone valve might give you a little bit of play, but not, if you're up here in terms of your intersection, not going to help you much at all in that case. And, and this is, again, the interesting thing about 3-speed circulators is when 3-speed circulators, they've been around for a long time. I remember using the B&G Upstart back in my contracting days, back in the late 80s. They've been around forever. But they really started to become commonplace in the early 2000s. And what happened was a lot of people started using them, believing that it was the only pump they'd ever need, believing it was the one pump to keep on the truck for service, and it does everything. But what they found was in zone valve applications, the zone valves would bang like hell. So what did the industry do? Rather than say, well, no, don't, in zone valve jobs, don't use this pump because it's the wrong pump. What the industry then said is, oh, well, the right way to do zone valves, because this is what the Europeans do, would be to put in a pressure differential bypass valve. You did put in a pressure differential bypass valve, didn't you? Well, no, I didn't know I had to. Well, you did it wrong. So now it became not only let's put the wrong pump in, but let's put a Band-Aid on a self-inflicted wound to make it work right. When really all you needed to do was use the right pump in the first place, which would have been a flat curve pump. So it's just interesting how things evolve over time and how, if you look back on it, through the lens of history with a critical eye, and you see, how the heck did we come up with that? Why didn't we just do this, which was the easy, simple, and least expensive solution? Why did we create a problem and then why did we try to solve a problem that didn't exist? And then when that solution to a problem that didn't exist created another problem, well, let's create another solution that costs more money. And then we go to the illogical stretch of when variable speed circulators came down the pike. Guys are saying, well, if you compare the price of a 3-speed pump and a pressure differential bypass valve, it offsets the cost of a variable speed pump, therefore problem solved. Again, not quite the right correlation. And it's also means you're missing out on some of the real benefits of a variable speed circulator. So a lot of interesting ways to look at this. And I hope this part proved helpful to you, at least illustrative, is that 3-speed pumps do have a place, but boy, oh boy, you got to pick and choose, and you got to know what you're doing and why. But that's true of anything, right? That's true of what boiler you choose. That's true of what air separator you choose. That's true of how you size your pipe and how you pipe up your boiler and where you place components in the system. All of those matter, right? They all matter, as does the pump you choose. It's very funny that we'll go to great lengths to well, I'm going to use this high performance air eliminator, right? I'm going to use this high performance air eliminator because even though it's more expensive, it's the best there is, and I make sure I don't have any air problems. And oh, by the way, I'm just going to throw this pump in here and set it on high because it works. We apply a lot of critical analysis to one part of the job, but not to all other parts of the job. So that's, again, just a way for you to think about what it is we're doing here. And just to give you an idea, some the Takeo options here when it comes to 3 speeds. Again, the 0015 3-speed, okay, is kind of your fighter pump. You got most of your residential applications are going to fall in there. Again, when you're using zone valves, I want you to think about whether that's the right pump for you or not, because more often than not, it might not be. But for radiant floor heating applications, for baseboard applications, for indirects and things like that, more often than not, you're going to be right in here, and that's going to make this a very good circulator for those applications. Zone valves, again, keep that asterisk there, but in all others, this is where it's going to make some sense for you. Now you get into bigger applications. Now you get into the 0013, okay? Some snow melt applications, larger indirects, maybe when you're dealing with heat exchangers, or really, really big residential applications where maybe you got to get way the heck out here, 15, 16, maybe 18 or 19 gallons a minute, or in this area where the head is higher, okay? So there's your 0013 application for you for a 3-speed option, all right? And then we get into flatter curve pumps, so that they don't look really flat here. You just want to make sure that the ratios are right, because here we're talking about the 0010, okay, which we saw earlier. 6.5 feet ahead out to 17 gallons a minute. If we change the perspective here, you'd see that these are flat curve pumps, even though they don't necessarily look like it. Okay, because if we overlaid the other ones, they'd be kind of like this. All right. So you have the 0010 3-speed circulator. Again, if you got a lot of B&G 100s or old Taco 110s in your service area and you're thinking about a pump to keep on your truck for service, and you know those are the kinds of jobs you go looking at, 0010 is really not a bad pump to keep on the truck for service. And it has a 4-way flange, so it doesn't matter what the flange orientation is, it'll fit. You get into larger applications of high flow, low head, flat curve pumps. Then we have the 0012 3-speed, which this one, again, it's 14 feet ahead, but it'll go out to 46 gallons a minute. So sweet spot wise, we're talking, mid 20s for flow and maybe 11, 12 feet ahead. So that's kind of where you're at with that particular circulator. Okay, has very, very specific applications. We try to get you both ways. We've got you covered from pretty small up to pretty large in the flat curve family, as well as pretty small up to pretty large in the steep curve family. So they cover a lot of different applications. It's not a matter of one pump to rule them all. It's a matter of which one of these best fits the application you're looking at, because no matter how we try to simplify things, that's really as simple as we can get. Which one of these circulators is going to best fit the applications I'm looking at? So instead of 12 single speed circulators, you have 4 3-speed circulators to choose from. And really that's about the level of simplification that we want to try to get to. All right. Cool. Now here's some basic guidelines. I want to just, for your 0015 3-speed, if you're looking for, hey, someone mentioned earlier, I'm in a house, I don't know all this stuff. What do I do? What do I do? These are just a couple of basics to keep in mind that will probably work for you. And it's going to be zone pumping fin to baseboard. So each zone has its own circulator, because that's about the extent that we can give you these basic guidelines. If my load is 40,000 BTUs or less, and the measured length, before we multiply by 1.5, if the measured length is equal to or less than 120 feet, the measured length is less than 120 feet, I'm good with low speed. You can math that out as many ways as you want. You're going to be good at low speed. So 40,000 BTUs or lower, 120 feet or shorter, you're good with low speed as a zone pump. Same BTUs, less than 40,000 BTUs and less than 235 feet worth of measured length, well, then you can bump it up to medium speed. Same BTUs and less than 290 feet, that's when I'll go to high speed. All right, so just some lengths that are kind of applied to using that math formula, measured length times 1.5 times 0.04, all right, is going to, if we keep those in mind at 4 gallons a minute, that's your 40,000 BTUs at 4 gallons a minute. That's about the farthest I'm going to be out there. Then we're talking, we can use these guidelines for low or medium or high. Okay. Good question. Is there a cross-reference chart out there? Actually, we have a cross-reference chart on the box of the 0015 for you to take a look at. So so that's, if you're looking for it, it's right there on the box. And if you need anything else, we don't have them on our website, but they may be others out there. But it's right on the box for a 0015, your cross-reference chart. Very good, very good. All right, how are we doing for question there? Other questions there, guys?
Good. There's one clarification. People are looking at maybe defining what the sweet spot is, because there was one question that related to that. Just remember that right in the middle of the pump curve, right smack in the middle, kind of the filet mignon, that is where the pump's going to be at its highest efficiency. We call it the best efficiency point. You can go a little bit to the left of that, a little bit to the right of that, but just, that's, if you're selecting pumps, try to get somewhere in there. And that should answer one of those questions. Dave, you want to take another one?
Sure. Question came in about biggest challenge is circulating pumps for underfloor heating, where high flow and head is needed. What do we suggest? Well, that is basically what the 0015 circulator is. Radiant underfloor heating is typically a low flow but a high head system because we're looking at smaller diameter pipe, but then we're distributing it across the entire room itself. So each loop is going to look at a low flow, but then you get higher head. So if you wanted to back up, John, into the 0015 curves, you'll see where that comes into play as a much better option, because now you have those 3 different choices in there. So a radiant manifold, if you're looking at, say, 1/2-inch pipe or 16 millimeter pipe, typical flow rate's about a 1/2 gallon a minute, per loop. You put a 4-loop manifold on there, that's 2 gallons a minute, but you're looking at maybe 7-8 foot ahead just in the pipe. Then you throw the manifolds, then you throw a mixing valve in there, and now you can see, looking at this curve here, 2 gallons a minute, 10 to 15, all the way up to 19, 17 foot ahead. So you have lots of choices in there and get it kind of close. Go up to 16, there you go, right? So you look at maybe
loops.
8 gallons a minute. Exactly.
Yeah.
So you're getting into the higher head. Yes.
Radiant tends to live right in that red circle, more or less.
Yep. When we look at a fin tube baseboard, or we look at cast iron radiation, now we're looking at higher flow but low head, big cavernous pipe, 3/4 inch, 1-inch pipe. So now we end up on the other end, outside that circle, on the right side of it, to the bottom of it. So that's where the 15 works into play, and then actually looking better at the flat curve pumps to look at there. So
John,
exactly.
do we have time for an opinion?
We always have time for opinions.
I think when I think about the 3-speed offering in anybody's flavor, let's talk Taco. It's still a fixed speed pump. John's already made that point. I'm going to remake that point, just saying, if I have a fixed speed pump, it doesn't matter if it's on speed low, medium, or high. It's never going to do anything automatically. It's just going to stay running on that, a monorail. It can't run anywhere but there. We take back to kind of circulator fundamentals. But if you have multiple things required of that circulator, like zone valves, telestats or actuators or stuff, then we want to start looking at, like John mentioned, a flat curve will stop the noise and velocity, keep those curves flat. But we're living in a world of variable speed circulators now that are delta P, and they can feel things happening. I wouldn't use a fixed speed pump, whether it's a single speed or a 3-speed pump, if I knew that I had something much better to offer. So again, if I'm doing a unit heater, if I'm doing a coil on an indirect, if I've got a boiler that doesn't modulate, etc., nothing varying in the system, use a fixed speed application for the sake of saving some money and stuff. But with all the technology that we have with variable speed now, use it when it's appropriate. And we've done all kinds of trainings on that. We have to bring some of that back. So anyway, hopefully I got it. Yeah.
I look at it similarly to you, Rick, other than the reality is there are a lot of folks that just that aren't using variable speed circulators, whether it's because of price, whether it's because of familiarity or understanding, or whether it's because of availability. It remains a fixed speed, either single speed pump or 3-speed pump world for them. And if that is in fact the case, well, let's just make sure you're using your 3-speed pump the right way.
Yeah.
Let's not presume that it's the only pump you'll ever need. There are still system dynamics at play that we really do need to understand. Very good. Some really good questions here.
Yeah,
Are 3 speeds just as reliable? Asked another way, do they have higher stress? Not really, Walter. That's a good question. We found tremendous reliability with our 3-speed pumps. Really, it's a single speed pump. You just pick one of the 3 speeds because it's not it's not bopping back and forth between anything. It's just a single speed pump. You set it to that speed and away she goes. So there's no real stress levels that are different compared to other circulators. So good question, Walter. So
the manufacturing process. Yeah, the manufacturing of a 3-speed circulator is relatively the same as a single speed circulator. The only difference that we have is we throw that switch on there, and the wires that come off the switch tap into different sections of the windings.
Yeah.
So we're not using all of the windings at one shot, and that's how we change the RPMs and change the speed of that circulator itself. So manufacturing is the same. Nothing else changes between fixed speed and single speed. It's just those tappings in there. Years ago, we used to have 3 separate windings in there to change the speed of the circulator. It was a much heavier circulator. It cost a lot more. The advantage that we used to have, as people would say, was, well, if it happened to die, if the motor died, you still have the other 2 speeds available that can get you through the night. But most people already had a replacement circ on their truck anyhow, so it was one of those things. Hey, you still got the phone call to come in. The homeowners were cold. You were standing there in front of it. Yeah, you found out that speed didn't work. What'd you do? Leave it? Probably not. And we pulled it out anyway. So we changed the process and now just went to a 3 different tappings that you have in the circulator.
Right, which is pretty much what everybody else in the industry does as well. They all have the same the same construction method of the tappings. Can the speed be changed while the pump is running? Yep, sure can. Not going to hurt a thing. Not going to hurt a thing. So we have reliability. Can you touch base on CV values of zone and mixing valves for pump selection? That's a great question. That's from Robert Benedicts. A CV value is a way of expressing pressure drop through a valve. Now I don't want to get too deep in it because this is a whole separate webinar, which we've done them on CV. And if you go to our website, you will actually find recordings of our previous webinars on CV. Just do a search on our website and on our video, our training library. But what CV is, it's a way of expressing pressure drop. Our zone sentry zone valve has a CV. Our 3/4 inch zone sentry zone valve has a CV of 10.3. Well, what does that mean? Is that good or is that bad? Well, what that means is if a zone valve has a CV of 10.3, that means it takes a flow rate of 10.3 gallons per minute through that zone valve in order for that zone valve to impart 1 psi of pressure drop on the fluid. And 1 psi of pressure drop is equal to 2.31 feet of head. All right. Now it's a 3/4 inch zone, right? 3/4 inch zone valve. The highest flow rate you're going to have through a 3/4 inch zone valve should be 4 gallons per minute. So 4 gallons per minute through a valve with a CV of 10.3, it's not a linear equation. It's actually algorithmic. The actual pressure drop through that valve is going to be minimal through the zone sentry. Now let's compare it to, let's say, a Honeywell zone valve or something with a spring return, a flapper that might have a CV of 3 or 3.5. 4 gallons a minute through a valve with a CV of 3.5. Well, that's going to add at least 2.3, maybe closer to 3.5 feet ahead, if not more, to your pressure drop through the zone. That's not included in that 1.5 times 0.04 equation. That's a situation where you're going to have to be very careful about calculating your head loss. Now it's a matter of not just knowing the math formula. It's what am I looking at? What do I see in the mechanical room? I see a flow rate of 4 gallons a minute, but I see a zone valve that I know has a low CV. I better take that into account when I'm selecting a circulator.
Yeah.
Need a little bit more, not fudge factor, but a little bit more headroom on my curve. It doesn't necessarily mean you automatically go to high speed. It simply means where do I end up when I do the math? And if I allow another couple feet for this zone valve, where does that take me? Am I still in medium or do I have to go to high? That's again the thinking in that process. Let me know if that answers your question, Robert, because that's a really good one. How else are we doing out there? Any other questions there, boys?
There's a ton of questions today, and what a great turnout too. Look at the attendees on that. So that's good.
Far out. Oh, here's one just came in. Is it normal for the pump body to heat up during operation? Oh, yes, absolutely. It depends on how hot it's getting. I mean, if you can fry an egg on it, we have an issue. We're probably working more on the high end up here in terms of flow and head than in the sweet spot, because we're turning that energy into something. So yeah, it will get they will get hot. They will get warmer because it's an electrical motor that's running. If it's running out here in the sweet spot, it will run cooler. If it's running up here, it will definitely run hotter. And that spending an awful lot of time up there will more than likely shorten its life.
We think about an AC circulator, we're looking at about 27% wire to water efficiency, meaning
Right.
27% of the electricity that comes into this thing is used to move water. All right, so there is a lot of electrical waste. It's the best we can get out of an AC circulator, being at 27%. Once we go to ECM, we can more than double that for you, but that electricity coming in has to be given off, and it's given off a lot of it by heat. So they will feel warm, especially if you have 180-degree water temperature that you're pumping through your house. So once you feel that, you could easily feel, I mean, 180 is, nothing to joke at when you're touching it. You touch the outside of that circulator, it's going to be warmer than that, obviously. So because it's not going to cool off into the water. So you could see 200, 210, 215 for the outside of a circulator. If it starts to get that hot, like John was saying, where the green paint's starting to turn a little brown, it may not be moving. It could be seized up. We're not, the impeller may not be spinning. Some of you guys may run into that, especially when we do startups in the winter after a system's been off for all summer and it may have seized up and that impeller's not spinning. It's going to get really, really hot. If you notice that, well, the first thing I want you to do is bang on it, wrap it, give it a wrap a couple of times to hopefully free it up to see what's seizing it up, or maybe there's something stuck in there. But they will get hotter at that point if it's not turning.
Here's one here. It says, what's the pressure drop calculation difference between balancing valve and motorized valve, which I'm assuming a zone valve, and there's not. I mean, you have to look at what the manufacturer said the CV was of both those items and use that in the calculation. Here's the kicker. When we look at CVs, the CV is always calculated with the valve in 100% open. If you start playing with a balancing valve and you start cranking that down, you're going to increase the pressure drop, and you don't know what the new CV is. So just keep that in mind. When we do our calculations and we look at CVs as part of that calculation, we're using the assumption that the valve's in the wide open position for pressure drop. So careful with that.
Very good.
Yeah.
Here's one. Are there circulator correction factors for the pump curves to account for viscosity changes in fluid? That's actually going to be done on the front end, Walter, I believe, is if we're talking GPM equals BTUH divided by delta T times 500. That 500 is going to have to do with the fluid at a specific temperature. In that case, we're talking room temperature, but it also takes into account the specific gravity and specific heat of the fluid. Now, when you start to add more viscous materials like glycol, all right, that's going to change the specific gravity and the specific heat, and that's going to change the 500 number. It's going to get lower and lower and lower. So that will have a built-in change, all right, in terms of doing that math, and it'll show up in gallons per minute. And then gallons per minute has a direct correlation into flow rate. And gallons per minute has a direct correlation into head loss. So it's kind of built into the math, if you will, based on what number you're using for that 500. 100% water at room temperature is 500. But the more you start mixing it, that's going to change that number. And that is basically looking at the jug of the glycol. What's the specific gravity? What's the specific heat? Then I got to figure out what the percentage is and do that math. Anything else we have in there? This is some really, really good questions, folks.
Good stuff. Yeah. Yeah. Dave's got a lot of them answered.
Who was looking for that head loss calculation. If you really wanted to know what the additional head loss was through the valve, that's it right there. If you look at my picture, the CV of the valve divided by the flow, then you square that and multiply it by 2.31. That'll get you the head loss, an additional foot ahead that you would add to what we had for the pipe before.
Very good. Sounds like that's a little in next go around or next quarter, we should revisit the CV webinar and do that one again. All right, and I just want to show you here real quickly the 0012 pump performance curve, as we said, lower head, higher flow, and then the 0013 higher flow, or higher head and slightly lower flow by comparison. So very good. All right, folks. as the lieutenant says, thank you very much. Oh, one more thing. No, we're not going to do one more thing. Not the Colombo thing. Any last minute questions, guys? But again, thank you very much for the gift of your time. We so very much appreciate it. And I hope everybody is out there staying safe, staying healthy, and most importantly, well, those are the two most important things, but also staying busy and keeping our customers warm and safe and healthy during what basically is spending an awful lot of time indoors this winter. So good luck to everybody. Stay safe, stay healthy, and thank you so much. Eric, thank you for the kind words. Really appreciate it.
Very good.
Very good. All right, guys. Any last words from you all, from Dave and Rick?
Just stay safe, be out there, stay in touch too. You know, you guys want to
That's
send
right.
us something? You know, if we didn't answer any of this stuff already, then Dave and I or John will get back to you and make sure we get them all answered. So anything I can do
Yes.
to help, send it to me. Okay.
You will get an email tomorrow showing you the link to watch this video again. So if you are sad tomorrow, you miss us, you want to hang out with us again, you can just rewatch it again and feel like it's all over again. Or even check out our the Takeo YouTube page, where we do have a lot of our webinars recorded if you wanted to get some clarity on some of the other things like John was talking about with CV and other details that you may want to check out. And and also take a look for the next future Takeo Tuesdays coming up. So thanks a lot for coming, guys.
Thank you all. Take care, everybody.
Thank you.